A very good afternoon to all of you. Guest speaker for today, esteemed faculty members and my fellow physics enthusiasts. Allow me to welcome you all to the fifth installment in the Physics Colloquium Postgraduate Series. I am Samiru.
And I am Shahara.
And we will be your compeers for today. So before we go in further, a small announcement. We will have a Q&A session at the end of this presentation. So if you have any questions, we are pleased to have a link open in the YouTube live chat and Facebook live chat. So if there are any questions you have, you can post it there. We will obtain answers for them in the Q&A session. Over to you, Sahara.
Thank you, Samir. Without further ado, let me introduce to you the guest speaker of today, Dr. Buddini Nissanka. Holding a bachelor's degree in biological science from the University of Kelaniya and a master's degree in analytical chemistry and a PhD in material chemistry and physics from the University of Colombo, Dr. Buddini was the awardee of the Astronomer Royal Sir Arnold Wolfendaire Memorial Gold Medal for being the best postgraduate student in physics at the Postgraduate Convocation in 2022. She also received the SLAS Postgraduate Research Merit Award presented at the 79th Annual Sessions Inauguration Ceremony at BMICH. Today, she will be presenting on the topic Structural Investigation of Graphene Oxide and its applications towards electrophoresis and hybrid material development, which is focused on the controlled synthesis of graphene oxide and its development for water purification, sensing, and energy-related applications. Dr. Buddini, the stage is open for you.
Everyone. First of all, I would like to thank Physics Society of the Department of Physics, University of Colombo, for inviting me for this postgraduate colloquium series to share my research work that I have carried out for my PhD research. So today I'm going to talk about the structural variations of graphene oxide and its application towards electrophoresis and hybrid material development. So with the rapidly growing global population, so there is a need for innovative solutions which can address the challenges in the areas of clean water supply, healthcare improvement, and the sustainable energy sources. So here, advanced nanomaterials have emerged as a promising avenue to address these issues. So one particular nanomaterial that has attracted significant attention is graphene oxide. So the synthesis of graphene oxide goes back to 1859. So even though its discovery over the 165 years ago, the significant attraction have been attracted from the chemical community for this geomaterial with the synthesis of with the discovery of graphene in 2004. So, reason for that is graphene oxide is one of the intermediates of the chemical synthesis of graphene. So, here I have shown the variation in the global graphene oxide market size over the years from 2018 to 2026, and this variation shows the growth in the global graphene oxide market size over these years. So, indicating the increasing demand for this material across various applications. So, this graphene oxide is a monolayer of sp2 hybridized and sp3 hybridized carbon atoms that are hexagonally arranged in the lattice. So, the basal plane of this graphene oxide is decorated with different oxygen functionalities such as hydroxides and epoxides, and then the carboxyls and carbonates. So, here hydroxyls and epoxides can be seen in the on the basal plane of graphene oxide, while carbonyls and carboxyls can be seen at the edges of the basal plane and the defects. So, due to the presence of these polar oxygen functionalities, the graphene oxide can be easily dispersed in water and other polar solvents. At the same time, this graphene oxide has high surface to volume ratio and can be modified, chemically modified or functionalized, serving these oxygen functionalities as active sites. So, because of these properties, graphene oxide is widely used for different applications such as development of sensors, then energy related materials, as well as for the water treatment and many more. So, as I mentioned earlier, so graphene oxide is one of the intermediates of the chemical synthesis of graphene. So, during the chemical synthesis of graphene, so graphite is oxidized into the graphene oxide and then followed by the reduction into the graphene via the chemical, thermal and electrochemical techniques. So, here obtaining this pristine graphene through this reduction process, through the removal of all these oxygen functionalities is highly challenging. So, that is like a dream. So, therefore, instead of that, a graphene like material that is referred as the reduced graphene oxide, which is RGO, with residual oxygen functionalities and the basal plane defects is typically obtained during this reduction process. So, here the properties of these reduced graphene oxide as well as the graphene oxide is highly depend on the structure of these graphene oxide. So, when it comes to the structure of these graphene oxide, so there is no precise or well defined structure for graphene oxide. So, the reason is the oxygen functionalities on graphene oxide are randomly distributed on the basal plane of these graphene oxide. So, therefore, this limits the reproducibility of geostructure for above mentioned applications as well as for the reduction into graphene oxide. So, basically the structure of graphene oxide is highly dependent on the type of graphite, the type of oxidant as well as the oxidation parameters such as oxidation temperature and oxidation time. So, therefore, controlling these oxygen functionalities during the graphite oxidation into graphene oxide as well as the reduction into reduced graphene oxide is highly important to realize their potential for real applications. So, in this research, I have first synthesized graphene oxide from high purity Sri Lankan vein type graphite using improved Harmer's method. So, that is the TAO method. So, here a series of graphene oxide samples was synthesized by varying the oxidation time. So, here oxidation time was varied for 1 hour, 2 hour, 3 hour, 4 hours and 12 hours in order to synthesize GO1, GO2, GO3, GO4 and GO12 samples respectively. So, after that all these GO samples thermally reduce into the reduced graphene oxide at 250 Celsius under vacuum conditions, and these RGO samples were named as RGO1, RGO2, RGO3, RGO4 and RGO12. So, after that the structural and chemical characterization of these synthesized graphene oxide and reduced graphene oxide samples were carried out using XRD and FTIR techniques. So, here I have shown the XRD spectra of graphene oxide as well as the reduced graphene oxide. So, here I have shown the XRD spectra for graphite, which shows the sharp and intense symmetric peak at around 26 degree, which corresponding to the 002 plane of graphite. So, that shows the highly crystalline structure of this graphite. So, when it comes to the XRD spectra of these GO samples, we can observe a new peak at lower angles around 10 degrees, which is corresponding to the 001 plane of graphene oxide. So, at the same time in these spectra we cannot observe any diffraction peaks at around 26 degrees, which is corresponding to the 002 plane of graphite. So, that means this graphite has been completely oxidized into these GO samples during the oxidation process. So, then after the reduction, the XRD spectra of these RGO samples shows broader and low intensity diffraction peak in the range of 17 to 30 degrees. So, this broader diffraction peak shows the amorphous structure of these reduced graphene oxide after the reduction process. So, that is due to the removal of basal plane oxygen functionalities during the thermal reduction process. So, when it comes to the FTIR spectra of these GO and RGO, the FTIR spectra of graphene oxide shows IR intensities that are corresponding to different oxygen functionalities. So, here we can see the incorporation of hydroxyls, then epoxides, then carboxyls and carbonyls into the graphene oxide during the graphite oxidation process. So, after the reduction of this same graphene oxide into the reduced graphene oxide, these FTIR spectra of these reduced graphene oxide shows a significant reduction in these IR intensities, which are corresponding to these oxygen functionalities. So, which is due to the removal of oxygen functionalities during the thermal reduction process. So, after that the structural variation of these GO synthesized graphene oxide and reduced graphene oxide samples was carried out using the methylene blue adsorption method. So, here methylene blue adsorption onto GO based materials has been widely used to remove the methylene blue dye from the effluent, as well as to measure the surface area and photocatalytic activity of these geo-based materials. So, here due to the presence of oxygen functionalities and the 5-bond conjugated structure, these geo-based materials have a strong affinity for methylene blue. So, therefore, methylene blue adsorption onto these geo-based materials is highly dependent on the structural features of these GO and RGO. So, therefore, in this study, I have used methylene blue dimolecule as a model molecule to probe these structural variations of graphene oxide and reduce graphene oxide during their synthesis. So, this is the first time that using this methylene blue as a probing molecule to analyze these structural variations of GO and RGO. Okay. So, here the methylene blue adsorption onto these GO and RGO was carried out by adding known and excess amount of methylene blue into the suspensions of GO and RGO. So, after the adsorption process, the remaining amount of methylene blue, which is in the supernatant, was measured using the UV visible spectrophotometer, and the amount of MB that absorbed onto this GO and RGO was calculated based on these UV visible results. And then the methylene blue adsorbed GO and RGO that was suspended at the bottom of this beaker was filtered and further characterized using the FTIR technique. So, in order to get the information about the interactions between methylene blue and these GO and RGO. Okay. So, here I have shown the FTIR spectra of methylene blue adsorbed graphene oxide along with the FTIR spectrum for methylene blue and bare graphene oxide. So, here in the methylene blue FTIR spectrum of the methylene blue, we can identify some dominant peaks of methylene blue, IR peaks of methylene blue, which I have listed here. So, here in the FTIR spectra of this spectrum of the methylene blue adsorbed graphene oxide, we can see the incorporation of these IR peaks that are corresponding to the methylene blue. So, which confirms the adsorption of methylene blue onto the graphene oxide. So, when comparing these peak positions, we could see that there is a blue shift in the C double bond C of the methylene blue after the adsorption onto graphene oxide. So, blue shift means here this wave number have been so this peak has been shifted to higher wave number. So, the most of the literature studies have reported this blue shift with the adsorption of methylene blue onto the surfaces in vertical orientations through the electrostatic interactions. So, here this observed blue shift confirms that the methylene blue is absorbed onto this graphene oxide in vertical orientation through the electrostatic interactions. So, then when it comes to the methylene FTIR spectra of methylene blue adsorbed reduced graphene oxide, this here also we can see the incorporation of these dominant IR peaks of the methylene blue, confirming that methylene blue has been absorbed onto the reduced graphene oxide. So, when comparing the peak positions of these dominant MBIR peaks, here we could see the red shift in all of these peaks. So, the literature studies have shown that. So, this red shift is associated with the adsorption of methylene blue onto the surfaces in parallel orientation. So here these observed red shifts confirm that methylene blue is absorbed onto this reduced graphene oxide in parallel orientation through the 5-bond interactions. Here these red shifts are possible due to the interaction of these methylene blue dimolecules with the remaining hydroxyl groups at the edges of the basal plane and the defects. So therefore, because of these interactions, the interactions are possible due to the adsorption of methylene blue in parallel orientation to this reduced graphene oxide through the 5-bond interactions. So therefore, these FTIR results reveal that methylene blue is absorbed into these GO and RGO in 2 different orientations. So here methylene blue is absorbed onto the graphene oxide in vertical orientation through electrostatic interactions, while it is parallelly absorbed onto the reduced graphene oxide through the 5-bond interactions. So these MB adsorption orientations are highly important during the measurement of surface area values. The reported studies in the literature, they have used the parallel adsorption of methylene blue onto these GO, both GO and RGO when they are measuring the surface area values. But here in this study, we could see that these methylene blue adsorb onto this GO and RGO in 2 different orientations, and we need to consider these orientations, the methylene blue adsorption orientations, when we are using this methylene blue adsorption method to measure the surface area of these GO and RGO. So then comes to the amount of methylene blue that absorb onto these GO and RGO. A significant variation cannot be seen in the amount of methylene blue that absorb onto these GO samples as the oxidation time is increased. The reason is all of these GO samples have the same amount of total amount of oxygen functionalities. So even though the same graphene oxide is reduced into the reduced graphene oxide, a prominent variation can be seen in the amount of methylene blue that absorb onto the reduced graphene oxide. So here, even though all these GO samples have the same amount of total oxygen functionalities, the spatial distribution of these oxygen functionalities are going to change with the oxidation time. So therefore, this change in the spatial distribution of oxygen functionalities is going to affect on the reduction process. So when comparing the amounts of methylene blue that absorb onto these reduced graphene samples, this RGO4 and RGO12 sample shows the high methylene blue adsorption. So this indicates the larger graphitic basal planes in these RGO samples. So therefore, the findings of this research provides valuable information to synthesize graphene oxide and reduce graphene oxide with controlled oxygen functionalities and larger graphitic basal plane. So this is highly important for the applications in the development of functional coatings, then electrode materials as well as the nanocomposite. So at the end of this study, I was able to publish these findings in the Journal of Materials Science. Okay. So then, based on the findings that related to the previous structural variation study, then I looked into the dye removal process using the graphene oxide as an adsorbent. So here use of graphene oxide as it is for dye removal as an absorbent is highly challenging. So, that is because the difficulties that associated in the separation of the dye adsorbed composite from water without adding any coagulant or flocculant. So, therefore, in this study, this graphene oxide is combined with the industrial waste sludge, which is having high disposal issues and no economic value, to obtain this geo-based composite. So, here this geo-based composite is used to treat highly toxic industrial dye such as rhodamine B based on the concept of waste to treat waste. So, in the preparation of this geo-based composite, the first aluminum hydroxide sludge was modified into the modified aluminum hydroxide sludge. So, here this aluminum waste sludge, which is discharged from the anodizing industry, is dried and ball milled and sieved to obtain the modified aluminum hydroxide sludge with finer particles. So, after that, this modified aluminum hydroxide sludge is mixed with a small amount of graphene oxide to obtain this geo-based composite. So, here after the mixing, this paste was partially reduced at 150 Celsius to obtain the composite with partially reduced graphene oxide. So, here for this geo-based composite preparation, I have used the 12-hour synthesized geo sample, that is the GEO12, because based on the results of the structural variation study, we could see that the RGO12 sample has the high methylene blue adsorption, so indicating the larger graphitic basal plane. So, therefore, for this preparation of geo-based composite, I have used the GEO12 graphene oxide samples to get the high surface area or the larger graphitic basal plane with this partially reduced graphene. So, here these modified aluminum sludge particles are positively charged. So, the charge was measured using the zeta potential values, and due to the presence of oxygen functionalities, this graphene oxide is negatively charged. So, during the mixing of this graphene oxide with modified aluminum sludge, this graphene oxide is coated on this modified aluminum sludge particles through the electrostatic interactions. So, then during the partial reduction at 150 Celsius, the sum of these basal plane functionalities are removed, restoring the graphitic basal plane. So, therefore, at the end of the process, we can obtain the geo-based composite with partially reduced graphene oxide. So, here I have shown the SEM spectra of the SEM image of the geo-based composite. So, here we can see the porous structure of these composite, so which is due to the porosity of the modified aluminum hydroxide sludge. And here we can see the flake-like structure, which is due to the incorporation of graphene oxide. So, then this the geo-based composite was analyzed for rhodamine B dye removal under different time period for different time periods, and here I have shown the UV visible spectra of these filtered solutions after the rhodamine B absorption process. So, here we can see that this geo-based composite shows the efficient dye removal even within 1 minute contact time. So, this shows the high dye adsorption performance and the efficient dye removal capacity of this geo-based composite. So, at the same time this geo-based composite shows efficient gravity separation. So, therefore, we can use this geocomposite to remove this rhodamine B dye to separate these dyes without adding any coagulant or flocculants. So, here the rhodamine B absorption onto this composite, geo-based composite happens via the two different pathways. So, first one is the presence of porous structure of these geocomposite. So, these pores can trap these dye molecules during the adsorption process. So, the second method is these rhodamine B dye molecules can absorb onto these partially reduced graphene oxide through the 5 bond interactions. So, then the effect of the pH on the removal of rhodamine B dye was measured under different wide range of pH values. So, here we can see that the adsorption of rhodamine B onto this geo-based composite shows an independent nature with the variation of this pH of this environment. So, that means there is no need of any pH adjustment during the dye adsorption process. So, at the same time by looking at these variations, so here we can see there is no independent, which is independent from the pH of the environment. So, that confirms that the methylene rhodamine B dye is absorbed onto these geo-based materials via the partially reduced graphene oxide through the 5 bond interactions. Because if there is electrostatic interactions are involved with this rhodamine B absorption, so then these rhodamine B dye removal can be greatly affected by the variations in the pH. So, here from this independent nature of this dye removal with the variation of pH, we can say that we can further confirm that the rhodamine B is absorbed onto these geocomposite through the 5 bond interactions. So, then the ionic strength effect on the removal of rhodamine B was measured by adding the sodium chloride, different concentrations of sodium chloride. So, here we can see that at low concentrations of sodium chloride, there is no significant variation in the dye removal process. However, at high salt concentration, we can see a significant increase in the dye removal process. The reason is the overall charge of this composite is positively charged, that was measured using the zeta potential values. So, here during this adsorption process at high salt concentrations, the negatively charged ions, so here that are the chloride ions, can screen the positive charge of this composite, reducing the repulsion interactions between positively charged rhodamine B dye molecules and the positively charged geo-based composite. So, eventually this will increase the rhodamine B absorption onto geo-based composite through the 5 bond interactions. So, then the rhodamine B leaching from the dye adsorbed composite was analyzed under a wide range of pH values. So, here we could see that this geo-based composite shows no leachate of rhodamine B back into water under this wide range of pH values. So, therefore, this dye adsorbed composite can be safely disposed or can be used to make building materials that could generate secondary income. So, therefore, this technology provides a sustainable and eco-friendly wastewater treatment and solid waste management method. So, at the end of this study, I was able to publish these findings in the Journal of RSC Advances, as well as I was able to publish this novel technology as a PCT application at WIPO. So, another promising application of graphene oxide is the use of graphene oxide as thin films or the coatings. So, among different deposition techniques, the electrophoretic deposition, that is EPD, is widely used to fabricate geo coatings with high homogeneity and control thickness. So, this is highly important for applications to control the coverage and the film properties with consistency. So, here during this study, the electrophoretic deposition of graphene oxide was carried out using a glass beaker setup under different EPD potentials. So, during this EPD process, this negatively charged DO particles move towards the positively charged anode under the effect of electric field and get deposited on this anode. So, during this same EPD process, we can observe the separation of this geo solution into a clear supernatant and a sediment over the deposition times as shown in this image. However, at higher potentials, we can observe the same sedimentation at the bottom of this beaker, but however, clear supernatant was not observed at high potentials like 15 volt and higher than that. So, this sedimentation is due to the combined effect of electrophoresis and water electrolysis that protonates the geo particles at the anode. So, here I have measured this sedimentation rate with by applying different voltages, and this is the variation of this sedimentation rate with respect to the applied voltage. So, here it can be observed an increase in this sedimentation rate with the increase of applied potential before reaching a steady state at potentials greater than 20. So, this sedimentation is highly depend on the applied voltage. So, after that, the morphology of these geo coatings that deposited under different voltages was measured using the SEM, that is the scanning electron microscopy. So, these are the SEM images that obtained at high voltage and the low voltages, and during the EPD process, the change in the geo concentration within this electric field region shows a dominant effect on the coverage of these geo coatings due to the sedimentation process. However, at higher potentials, this delamination of these coatings due to the evolution of gas bubbles with water electrolysis limits the growth, homogeneity and the stability of these geo coatings. So, then when it comes to the chemical structure of these geo coatings, So, here I have shown the FTIR spectra of these geo coatings that deposited under different deposition times and different deposition voltages. So, in these FTIR spectra, we can observe the IR peaks which are corresponding to the oxygen functionalities of graphene oxide. So, that confirms that the presence of graphene oxide in these geo coatings. However, when we look at this FTIR spectra, we can see that the IR intensities of these, the intensity of these IR peaks is going to increase with the increase of deposition time and the deposition voltage. So, this is due to the increase in the amount of graphene oxide that deposited on the anode with the increase of deposition time and the deposition voltages. Then comes to the XPS analysis of these coatings. Here I have shown the XPS carbon 1s XPS spectra of these geo coatings that obtained at the initial stage of the deposition and the end of the sedimentation process under different voltages. So, here in the geo coatings that obtain at the initial stage of deposition under low voltages shows the less amount of basal plane oxygen functionalities. So, this basal plane oxygen functionalities are shown in this blue color peaks. So, this less amount of oxygen functionalities can be observed in this geo coatings that obtain at the initial stage of deposition at low voltages when compared to that higher potentials. At the same time, these geo coatings that obtain at the end of this sedimentation process shows the high amount of basal plane oxygen functionalities. So, when comparing the both coatings that obtain at the initial stage of deposition and end of the sedimentation process at 15 volts, they do not show any variation in the total amount of basal plane oxygen functionalities. Basically, these two coatings shows the same amount of basal plane oxygen functionalities. So, during the EPD process, the smaller geo particles with less amount of oxygen functionalities get deposited on the anode at first, and then the larger particles with high amount of oxygen functionalities get deposited on the anode later. So, here these variation in the amounts of basal plane oxygen functionalities in these coatings is due to the size selective deposition of graphene oxide, and which is influenced by this sedimentation process. So, then comes to the chemical structure of these sediments that separated under different EPD potentials. So, here I have shown the FTIR spectra of these sediments that separated under different voltages, and in these XPS spectra we can see the same IR peaks that are corresponding to the oxygen functionalities of graphene oxide. So, this confirms the presence of graphene oxide even in this sediment. When it comes to the carbon 1s XPS spectra of these sediments that separated under the different voltages, here we can see the similar amount of total basal plane functionalities among these three coatings. However, the amount of basal plane oxygen functionalities in these sediments the functionalities which are in these sediments are less than the total amount of oxygen functionalities that present in the geocoatings that obtained after the sedimentation process. So, during the sedimentation, smaller geoparticles with less amount of oxygen functionalities are protonated and sedimented at first. However, the larger particles with high amount of oxygen functionalities protonated and get deposited, get sedimented at later, because they have the high negative charge and the protonation is difficult. When it comes to the large geoparticles with high negative charge, they are more stable in this geoelectrolyte and they more like to retain in this geosolution. So, therefore, these geoparticles with high negative charge get deposited on the anode at the end of this EPD process. So, therefore, the findings of this study provides new insight into the geoelectrophoresis as well as highlighted their effect on the stability and chemical properties of these geocoatings. So, at the same time, this by properly applying these EPD parameters, this geosedimentation process can be, geosedimentation method can be used to separate graphene oxide from bulk solutions during the synthesis of graphene oxide and their derivatives. So, at the end of this study, I was able to publish these findings in the Journal of Materials, Chemistry and Physics. So, at the same time, this geosedimentation method, which is used to separate the graphene oxide from bulk solution, was patented in Sri Lanka. Okay, so, these are the main outcomes of this research. So, from the structural variation study that provides the valuable information to control synthesis of graphene oxide and reduce graphene oxide with larger surface areas. So, then the composite developed from this graphene oxide and the industrial waste sludge provides a sustainable and environmental friendly wastewater treatment and solid waste management method. So, the geosedimentation method presents a new insight into the geoelectrophoresis and associated structure and surface properties of these deposited geocoatings. At the same time, it provides a cost-effective and scalable method to separate graphene oxide from bulk geosolutions. So, the financial assistance for this research was given by the research grant of University of Colombo. So, at the same time, I would like to thank all the academic and non-academic members of the Department of Physics, University of Colombo, for the support that given to me in order to complete this research. At the same time, I should mention all of these institutes and departments for the instrumental facilities that given to me during my PhD research period in order to complete this study without any hindrance. So, that is the end of this presentation, and thank you very much.
if there are any questions from the live audience here. Okay, then we will be
I have a question about graphene oxide in general. So, is reduced graphene oxide more like similar to the original graphite
Reduced graphene oxide, more
Yes.
similar to the original graphite?
than the
No.
GO?
No, no, that is different than the graphite, because even if you see the XRD spectra, you can clearly see that graphite has the more sharp and intense XRD peak. So that shows the crystalline structure of the graphite. But when it comes to the reduced graphene oxide has the amorphous structure, so that shows the broader diffraction peaks with low intensity. So that means the graphite has the crystalline structure, but when it comes to the reduced graphene is more amorphous structure.
But the graphene oxide's XRD peak was situated near the peak of the graphite, right?
No.
It was in the 20s, right?
No, graphene oxide is in the lower diffraction angle, that is the 10.
Sorry, the GO that is in the 20s, right?
Graphite is in the 26. This one. So graphite is in the 26 and graphene oxide is at the lower diffraction angle, which is at the 10.
But RGO is in the 20s.
Yeah, it in between 17 and 30. Here we cannot observe any sharp peak, but it is a broad peak.
So can we say the planes are planes
But
of
it is not,
RGO?
no, it is not similar to the graphite.
Thank you, Miss.
I know very little about this field.
Yeah,
So this RGO1, RGO2, RGO reduced graphene oxide 3, 4, and then all of a sudden 12. I mean, why did you select those? I mean, RGO after RGO4, is there a particular reason to go to RGO12?
no, sir. Actually, normally the improved Harmers method is carried out for 12-hour synthesis. So basically, we wanted to go to the oxidation time, which was less than the 12-hour oxidation. So that's why we selected 1 to 4 hour synthesis. Then when we compare these results, we could see that so the GO4 and GO12 has the similar kind of properties, and so there is no need to go beyond beyond the GO4.
Thank you.
Only for characterization, or have you identified any like applications for using
No,
that technique?
I think I have described that. So here, normally methylene blue adsorption method is used to remove the dye, methylene blue dye from the effluent using graphene oxide as an adsorbent. At the same time, methylene blue is also used to measure the surface area as well as the photocatalytic activity of these geo-based materials. So, those are the applications of MB adsorption with the graphene oxide. But in this research, I have used this methylene blue to probe the structural variations of these GO and RGO. These are the applications.
So those two have the difference of having methylene blue binding vertically and horizontally.
Sorry, I didn't get the question. Can you just?
Can you go to the previous?
Yeah.
The one with the variation in the binding. Yes.
This one.
Yes. So, are there any like identified applications that use this behavior of having methylene blue binding vertically and horizontally?
Not directly, but we can use this for the surface area analysis part. So, when we are measuring the surface area using this methylene blue, we have to consider these two orientations of MB absorption onto GO and RGO, because based on this orientation, we have to calculate the surface area values. Otherwise, if you use the similar orientation for both GO and RGO, then the values are not correct. So, these two orientations mainly can be used to measure the surface area of these GO-based materials.
Thank you, Miss.
Thank you, Dr. Buddini. Please remain on the stage for a small token from Department of Physics. I invite Professor IMK Fernando to hand over the
And now we have come to the end of today's proceedings. So I would like to take this opportunity to thank everyone who helped make this event a reality. First and foremost, I wish to thank our guest speaker for today, Dr. Buddini Nissanka, for sharing her valuable insight and findings with us. Next, I will thank Professor Dilushan Sundara, who was Dr. Buddini's PhD supervisor, for his guidance when organizing this physics colloquium. Our fond regard goes to Dr. Lakmal Veervarna, the senior treasurer of the Physics Society, and Professor Chandana Jayaratna, the head of the physics department. Our appreciation goes to Professor IMK Fernando and Dr. Kanishka Vijayaratna for gracing this event with their presence. This event would not have been complete without the support of FOSS Media, which is the media unit of this event. And last, but certainly not least, our appreciation goes to all the lecturers, research assistants, and students who participated with us today, and all who joined through YouTube and Facebook. This marks the end of the 5th Physics Colloquium. Have a nice day.